if you want to have the probability of your miracle larger than your mundane claims, mathematically you have to have the mundane claims explain the data so much worse than or basically comparably worse than the miracle itself. And so this is what it means to have extraordinary evidence is the fact that you need to rule out nearly every other mundane claim. Not just that it's unlikely, but you have to get it to the point where it's nearly ruled out. So that's what. So Carl Sagan had this pithy quote, right? And you kind of
So guys, thanks for coming to our talk today. I just wanted to briefly introduce SSOMIT and our speaker. So guys, my name is David, and I'm the president of the Secular Society of MIT, or SSOMIT for short. We're a group of humanists, agnostics, and atheists at MIT, whose mission is to provide a space for our community and to advocate for issues such as science education and religious freedom. I'd like to introduce our speaker today, Professor Brian Blais. Did I pronounce that correctly? A professor who is a professor of science in the School of Health and Behavioral Sciences at Bryant University in Rhode Island. He has a PhD in physics from Brown University, and for many years was a visiting professor in the Institute for Brain and Neural Systems at Brown University. His focus has been on computational and statistical methods applied to a wide range of fields such as the neuroscience of vision, paleoclimate, disease modeling, and most recently, the textual properties of the New Testament. He has a personal interest in science education and maintains a blog at https://bblais.github.io, where he explores the intersection of science and society, often dealing with issues in religious thought and pseudoscience. He is the author of the book, A Measure of Faith, Probability in Religious Thought. Also, we will be having pizza in like 15 minutes once we reach you guys here. Okay, without further ado, Professor Brian Blais.
Good evening, everyone. Hopefully you can hear me all right. Sounds good. So let me just start over here. That's essentially who I am, and so most of my writings come on my blog. That's something I'll see for that. So I'll start with my religious story. And so I was brought up Catholic, and I've moved away from the church. I would say in high school, being kind of a deist in early college, and an atheist later in college. And I'm happy to talk about any of those details, if you're interested. So I may be asking questions along the way, audience participation, and but I definitely take any questions, interrupting me, if we want to go into detail of anything that we want to look. I've always been a strong proponent of scientific thinking and education, so I like to report areas in that way, but I enjoy exploring perhaps some of the more entertaining aspects of things, UFOs, alien abductions, those sorts of things, but also looking at pseudoscience and how people fail in rational thought, cognitive biases, and those sorts of those sorts of things. So, to rough outline what I'm going to do, I'm going to introduce a probability notation, walk through a simple example just to kind of get both kind of notation and the approach that I use on all these problems, and also kind of build an intuition and then build up a vocabulary that we can use to talk about a whole bunch of other problems. And then I'm going to start looking at various examples from resurrection, from the existence of God, from evidence and testimony and faith and trust and all these sorts of concepts. And then again, if you have any questions as we go, let me know. So there are a lot of introductions to probability, and my inspiration comes from E.T. James. Has anyone ever read any E.T. James? This is one of my favorite books of all time. My copy of it is well worn. It's about yay thick. But one of the interesting things about his approach is he starts with a set of axioms that seem somewhat non-mathematical. I mean, the degrees of plausibility represented by real numbers, a qualitative correspondence with common sense, essentially a consistency with Boolean logic. if a conclusion can be reasoned in more than one way, then it should come up with the same probability assignment. Equivalent states of knowledge are given equivalent probability assignments. The probability value is a measure of our state of knowledge, and so on. And these seem like they are kind of non-mathematical, but he is able to then from these prove the essentially axioms that we're familiar with probability. And an interesting corollary of that is any approach that violates any of the rules of probability will then violate one of these axioms. And so we can see then probability as essentially a generalization of logic to cases where there's uncertainty. So I just see probability theory as how do we think rationally? And sometimes it's with numbers, sometimes it's just the structure that's enough. So that's why. So these are the essentially the consequences of James' axioms. These are often given as axioms themselves in some treatments of probability. But this gets into some of the notation that I'll be using. So probability of A being some proposition, probability of A is 0, then we're certain something is false. If it's equal to 1, we're certain it's true. This will only exist in cases where we are proving something literally, like a geometric proof starting from axioms of Euclid. Anything else will be between 0 and 1. We have the various mathematical rules, the sum rule, the product rule, and so on. And then at the last, we have Bayes' rule in this particular form, and it takes a number of different forms. And the left-hand side of the world we call it posterior. The right-hand side has the likelihood and the prior. The prior is essentially prior to your observations, and then we have a normalization at the bottom. Now, so how many of you are very familiar with these equations? So that'll help me give you some. So some very familiar, and some a little. Okay, that's good. That's pretty much where I'm targeting things. One can think of, I did a TED talk where I talked about Bayes' theorem without math. And so one can also think of it this way, where your belief in a particular claim or explanation should scale up with how well your explanation fits the data or explains the data. It should scale by how plausible that explanation you had before you observed the data. But it should be scaled down by all the other ways that you could have explained the data, right? And we're going to keep coming back to this because in many of the explorations of Bayes' theorem and so on, they talk a lot about priors. They talk a lot about how the models explain the data. They rarely talk about or stress the alternatives, and we'll see how the alternatives can make a big difference in this. So I'm going to use a very specific example to help walk through both the kind of notation I'm using, but also to gain an intuition for how this plays out. So imagine we have these two decks. I'm calling one the low deck and one the high deck. And someone tell me why the one on the left is the low deck and the one on the high is the high deck. Yes, I'm going to start calling on people. Yeah.
So the low deck has more than low number of cards, right?
Right. And so kind of from intuition, if you happen to have one of these decks, if you happen to draw a high card, you might think that you're more likely to be holding a high deck. Or if you draw the low card, low cards come out of that deck more often. So imagine you're given an unknown deck. You don't know what it is. It's either the high or the low deck. You take draws. That's essentially your data. And after each draw, you reinsert the card and reshuffle it. Now, we could do it where we set the card aside, but I'm going to do this for a particular reason, both for kind of mathematical simplicity, but also for there's a pedagogical point here. And my data is the following. I've drawn 2 9s. So I've drawn a 9, noted it, threw it back into the deck, reshuffle, pick it up, do another 9, and then that will and that's my data. Now, your intuition should probably tell you whether you are leaning toward I'm holding the high deck, I'm having the low deck, or basically 50-50. So what should your intuition actually tell you in this case? High deck. Should be high deck, right? So and now is it like, are you absolutely certain that it's the high deck? No. So you could so we have essentially grades of uncertainty. We'll probably start off, essentially, because you don't know anything, you just have 2 decks, about 50-50, and then we've done these 2 draws. So there's intuition, and there's essentially our data. I'm just going to summarize instead of having the pictures, kind of how many of each of those numbers there are in the deck, so that way we can do this. So we'll keep coming back to this, but the decks that we're comparing, so, I'm trying to ask, am I holding the high deck or the low deck? These are what I call models of the world. I'm trying to say something about what the world is like, and we use the same vocabulary in pretty much every context. The draws of the card, that's the data that we're taking, things that the evidence that we might be using, and the goal is often to find the most likely model given the data. Okay, so this is the structure of Bayes' theorem, and I wrote a book called Statistical Inference for Everyone that is kind of an intro stats textbook, and you can download it off of my website. It's free. You can order on Amazon, for a small fee for the printing cost, but you can get the PDF for free, and in that book, I write out Bayes' theorem in a way that I've not seen in other places, so that's why I want to talk about it here. A lot of textbooks will take Bayes' theorem, and when they're comparing multiple models, you'll find that the denominator of Bayes' theorem gets really, really long. And so if they try to do like 3 models, it becomes like the denominator becomes the entire page, and they can't really print it on the same page. And so what happens is most textbooks just restrict themselves to 2 models, not because the approach can't handle more than 2 models, but because you just can't fit them on the page. So what I prefer to do is the following, because it's the notation. So I have the left-hand side of Bayes' theorem here. I don't do an equal sign because I'm just doing the numerators. So I said I'm just going to do the numerators of Bayes' theorem, calculate out those values, add them up separately. So I essentially do the calculation in 2 steps, and then go back and redivide. And I'll kind of show you in this problem how that works. Okay. So here's my I've drawn 2 9s. And so I'm looking at the probability that I'm holding the high deck, given that I've drawn 2 9s, the probability of holding the low deck, given that it's 2 9s, and then the Bayes' theorem has it in terms of the likelihood, which I call the easy problem. Essentially, if you know that you have the high deck, then you know that the probability of drawing a 9 is 9 out of 55. So because you know about what the hard problem is always, am I holding a high deck or a low deck? But that's the part that's unknown. So Bayes' theorem is really translating kind of the easy problem into the hard problem, one that we're more interested in. The prior probability is essentially what we knew before the data. So we have knowing the size of the decks. There's 9 out of 55 for the first draw. The mechanism of taking data makes the next draw independent of the previous ones. I could imagine a case where, I had, instead of a deck, I just had those 55 cards laid out on a pile, and I took one and looked at it and just kind of tossed it back. That might make it more likely I'd pick up the same card, right? So one draw might be dependent on the next one. But in this case, we're going to assume that it's independent. And so then we have essentially 2 independent draws of 9s. There are only 2 9s in the low deck, so we get 2 out of 55 in those cases, and then times the prior. We get calculate out what that number is. That's not an active probability, it doesn't add up to 1. We then sum those values, go back, and we divide, and we get the final probability. So having drawn 2 9s, I went from 50-50 to about 96 and 4%. Right? So and that tracks our intuition. Right? So I like doing these small problems to kind of tease out our intuitions, and there's going to be a number of other small problems that I'll do likewise. But it's helpful to look at this. So I can do the same thing, imagining that I take, I pick out a 9, and then I'm like, oh, that's interesting, and note that, I throw it back in the deck, reshuffle, pick out another card, oh, it's a 9, okay, great. I do it again, I do it again, I keep getting 9s, and there's 5 9s in a row. Okay, I can do that. I can just do the calculation, and now instead of 96 and 4, I'm 99.95% short, right? That I'm holding a high deck. Right. Let's imagine I keep doing it, and I do it and I do 10 in a row. Is there anything wrong with my math? And 10 in a row, I'm like, now 98.99997% sure that I'm holding the high deck. Is there anything wrong with my math here? Is there anything that's not according to your intuition? Does your intuition say something's wrong with this example?
No, it's all right.
So you really would think that you were 99.9999% sure that you're holding the high deck having drawn 10 nines in a row.
Yeah, I would say so.
Now what if I did it for 20? Right? Each time I'm just drawing a 9, right? And I'm drawing a card, noting it's a 9, and then reshuffling and taking another one.
I think it's what you're saying. So are you saying that like I should think like outside the box and like
okay, like what?
So like there's a possibility outside the two you gave me, right?
Okay, so suddenly that idea starts coming to your head, right? Now, does that occur at 5 nines or 10 nines or 20 nines? Who knows what, right? At some point, you start becoming suspicious that I've lied to you. All right? I'd like to do a demo in my classes when I introduce probability. I happen to have a quarter that has 2 heads on it. All right? And so I like to bring out that quarter and just say, oh, I'm just going to flip a coin a few times to get some data. And then we start flipping heads. And I just see how long does it take before they start becoming suspicious? Because at first they think it's fair. But then after a while, you're like, wait a minute, something's up, right? There's another model out there. Okay? So you can imagine that maybe that you have a 9s model, right? They're basically, we're highlighting the fact that, like, okay, the high and low may not be the only thing. There might be some trick in terms of my reshuffling. I could be a magician. It could be that I happen to have a deck that's a 9s deck, right? That's the thing. The fact that it didn't come up initially, meaning it kind of wasn't on my radar, meant that it was a low prior. Your brain essentially had that at a very low prior, way lower than high and low deck. You basically were trusting, but you had that kind of in reserve. So it's a possibility that it happens. But I can do that. So we'll imagine that I had, now I use another model. I have high and low. The priors still have that up to 1, but like the high and low deck priors are basically 50-50, and the 9s deck one is way lower. Okay? And then as I keep drawing 9s, what can happen is, and this is after 2 9s, we're still not particularly likely that we have the 9s deck, but it creeps up. And so this is the picture where essentially I start with a prior for the 9s deck at 1/1,000,000, and then I keep drawing 9s, and then what you notice is that the high deck initially becomes more likely. We basically say after a few 9s, you're like, yeah, I'm definitely holding this high deck. This is definitely me. And then after a few more 9s, you're like, okay, something is up. And then after a while, you're like, there's no way that's the high deck. Right? So your position changes. And so I like to start with this example because one, it's not an example that's often shown in a lot of textbooks. They usually limit themselves to 2 models. And it's also not generally shown to have priors that aren't equal at the beginning. And it's also not often explored in cases where 2 models kind of cross over. You start believing in one, and then keep taking data, and then you suddenly slide into a different one. Right? And this is kind of something that you kind of keep in your head as we look at other examples. So there's a number of lessons here, and then I'm going to show an example from the kind of apologist literature. And so you notice that the probability of various models may depend on the alternatives even more than the data. So the fact that we can introduce an alternative, the 9s deck, change the way that the probabilities work. What we call data has to be carefully considered. So I didn't say that there was definitely a high and a low deck. I said that you were told there was a high and a low deck. And then what that does is introduce also kind of a layer of, okay, do I trust who's telling me? All right, and so being, so we have to be careful about how we actually define our data. And even if we said there's definitely high and low deck, this is the speaker talking, so someone is actually telling you this. Even a model with very low prior can become really likely if the conditions are right. The event is very rare. statistical independence, we assumed it in this, we kind of constructed it. Yes?
If you start with a prior of Pn equals 0.
Okay, you can never recover it.
Right.
All right. So any prior that something is equal to 0, right, should really be restricted to those things that have a logical contradiction. You know, a married bachelor has a probability of 0. All right, it may even be ill-defined. You also have to make sure that your propositions are well-defined. That could be an issue. But assuming it's well-defined, like a squared circle, that kind of thing, you know, something that has a logical contradiction would be 0, and that should be the only thing that's 0. All right, and so if someone says there's no amount of evidence that will convince me, then you know they're being dogmatic, and that's kind of the definition of being dogmatic is that you assign a prior that is essentially 0, that no amount of evidence will actually sway. But you can think of all sorts of crazy ideas that have like effectively 0 prior in most situations, but you could, with sufficient evidence, actually come to believe it. Right? And you should always be able to ask yourself that question: is there any way, in principle, you would come to believe some proposition? And the answer should, unless there's a logical contradiction, the answer should always be yes. You should always be open to it. Sometimes people say that, like, you know, skeptics just, you know, refuse to believe in miracles. Like, you know, that miracles simply can't happen. The probability of 0. And some people will say, you know, and there are even some skeptics who will say there's no amount of evidence that convince me that a miracle happened. And it's like, yeah, that is dogmatic. Right? You know, I don't believe in miracles. I think that nothing has ever been even remotely close to being demonstrated. But one should always be open to the possibility. You may have a super low prior, but that means that you need to have special conditions in order to bring that prior up to that. Another interesting thing about this particular problem is that you can introduce data that's more likely on a given model. So drawing the 9 is more likely on the high end, right? And yet the probability could go down because it could increase the probability of an alternative even more. Right? So it's not enough to say that, like, oh, it's really likely on my model that I got this data. That's just not nearly enough because you need to have So jumping into a case paper by Tim and Lydia McGrew. This is a paper on the argument for the resurrection based on miracles, and they do they write out Bayes' theorem. They have they put some numbers in there. They have a conclusion. Essentially, the models of the world that they put there's the resurrection model and the not resurrection model. I find that a lot of apologists will like to make things into 2 models rather than think in terms of multiple models. I'm not sure exactly why that is. I think it ends up making things a little less defined. Their data is that, you know, women found the tomb empty, which they consider to be unlikely. That 13 disciples, and it's the 12 and Paul they're including, saw Jesus after death, and that Saul/Paul was converted. I changed their notation a little bit for clarity. They actually used Paul, so they ended up having a P, and then they had a P in the parentheses, which is like really unclear in the paper. But anyway, so they write down Bayes' theorem, probability of resurrection or not resurrection, given the data. There's their data, and then they have the likelihood in the prior. Then they calculate out this ratio, which they do. They kind of essentially they take the 2 equations, they do the ratio of them. You can see each independent bit of the likelihood term. So the women, the disciples, they're considering them all independent, and we have 13 of them. There's the Saul's conversion. They put in numbers for each one, and they come up with a 10 to the 44 answer. And so they say that the resurrection hypothesis is like just outrageously more likely than anything else. Right? Now you can read the paper or read our review, go look at reviews on it to see whether I've mischaracterized this at all. But assume that I've characterized this okay, anyone happen to see any issues with the way this is set up? Anything that, if you think back on the lessons that I just showed in the previous example, that you might actually see here? Yeah.
It's assuming the given data is absolutely true.
Okay, yeah. So they're assuming the story is true, as opposed to the data should be. We have texts that say that women found it. We have texts that say that Paul was converted and so forth. Okay, so there's one level of abstraction there. They do this a lot in that paper. Okay. Other things. Now, there's one thing you might notice or not. If you look at the ratios, they have molecular tone for the women, the disciples, and Saul's conversion. Notice what they're missing. What's the last part of base there? The product. They completely ignore it. They just look at the likelihood. They're basically saying, on our model, the data is really likely. And it doesn't matter how unlikely the model was before it. Okay? So dropping the fire, dropping the data, and so on. So I have this list. So essentially, yeah, the data should be text with stories about these, that include each of those. The models may not be well defined because it rolls in a whole bunch of other things. Lack of imagination, and that's what I call like not looking at the alternatives, and that comes into play. The priors are ignored. Independence is not justified. Right? So in this case, we have can we believe that the disciples individually, all 13 of them, are statistically independent in terms of their testimony, even if it were true? And it's like so that's not justified at all. All right, so this is the sort of thing that I like to do. Is I like to, some of the papers and concepts are they actually do calculations. In other cases, they don't. How would we improve it? So just to kind of say, how would I do this if I were trying to do it right? We have had as many models as you want. Like for instance, you had the resurrection by Yahweh. We had to be specific about how a resurrection might happen, because you could include like a resuscitation by aliens. That would be all in there. And you might say, well, that's super unlikely, but you might also say the resurrection by Yahweh is also really unlikely. So they're dealing with fires in that case. You could say maybe because we have text, the stories of these, maybe the stories were entirely fabricated. Maybe they weren't fabricated, but they started with a vision and got embellished. James Fordower has a book called Unreasonable Faith, where he calls it RHBS model, which he talks about how the body was reburied, it was buried in a tomb, but then moved afterward. But there was a hallucination and cognitive bias and a socialization factor and so on. And so you can just list off as many models as you want to, and do essentially base them along the way. You have to address the prior probabilities for each of these things, and you could outline to do this properly in this way. This is how it probably should be done. So we actually you can get a lot of stuff up on my website. But I was on a Digital Gnosis YouTube channel a while ago. It was 2 years ago, maybe. 2021. Where we went through that entire paper. It's a fairly long paper, and the YouTube is about 9 hours long. So if you definitely play it on like 2 times speed. It was a little bit more interesting given the time zones involved, because Nathan's in around London, I'm in Rhode Island, Camille is in the Czech Republic, and James Porter is in Australia. So we met sitting at a Zoom meeting with that range of time zones. This talk is actually at a much more comfortable time than that was. So this is kind of my game, right? So try to map every concept possible in terms of probability, because I think probability is really just a description about how to be rational about anything. And it can be about aliens, it could be about medicine, it could be about politics, about anything. I don't have a huge interest in politics, I don't follow that as much, but definitely a lot of the other things, anything related to science. I find that it helps structure the your thought process. So it kind of points to the areas where things may be a little less clear. It makes explicit all of your assumptions. This is why I like kind of playing this game. And sometimes there's like unintuitive consequences of doing this. There is a danger of taking something that is not mathematical and making it mathematical and causing confusion or causing people to take you as an authority, even if your calculations are wrong. And so sometimes it gives you an air of authority even if the math is wrong, and you want to avoid that. But sometimes it can make much more clear where your uncertainties are and kind of the levels of where the probabilities are kind of quantitative. There's a whole host of books that deal with probability and God and in all its various forms, and so I've gone through a number of these, and there's concepts that come up along the way. So this talk is going to be a bit of a mixture of things. I've also been on a number of different podcasts talking about, I was on the Unbelievable podcast talking about faith and trust. So I'm still unbelievable, and talk about miracles. And you'll notice it's also about the resurrection, also about miracles. So I'm a basal atheist for talking about this kind of Bayesian in general. And then yesterday I was on Apologia and Vision talking about looking at the statistics of ancient Jewish texts. So so I can talk about any of those topics as we want to. Okay. So let's just go through a number of different examples and let me know where you think. So Richard Swinburne has this argument for the probability of God, and he comes up with essentially at least 50-50 on the result, and he has like 3 models that it has, and he has data that is here on the left-hand side. I am not a philosopher. I tend to find that the philosophy literature tends to be a little bit, the language I think sometimes can get overcomplicated and kind of needlessly so. But again, even here, so like they like the probability of God and the probability of nothing, right? So they have the two models. And to me, the biggest issues here are so he actually gives the reasons for why it's various models work. So the God hypothesis says the hypothesis of theism is very simple, simpler than the hypothesis of many gods. So he relied a lot on the idea of simplicity in his hypothesis, and then his other reasons are mostly about incredulity. We can't imagine how this would happen. But I look at these sorts of arguments, and I see the problems stemming from basically 3 issues, and I'm going to focus on 2 of them. One is lack of imagination. That's the alternatives, right? One is ill-defined concepts, and I think a lot of these kind of theist arguments that the actual propositions are not well defined. And the idea of simplicity, and I don't think I've seen any coverage of what that means really, and we can get some inspiration actually from Bayesian about what simplicity actually means. So lack of imagination. So it has like his hypothesis 1 is basically that there could be one God and that would explain it, and the other 2 basically they're saying that there aren't any. But you could have any number of different gods. So if they said a probability of God given my data, that could mean Yahweh from the Old Testament. That could be Stephen Fry's evil God. It could be the God that brings pizza, which just seems to have just appeared right here. Right? We could be Greek pantheons. We can have all sorts of other things. We can have multiple different non-God models as well. And we want to pause for a second and have pizza, and then
let's pause. Yeah,
that's good. And then I can also take questions as we're just milling around and so, but in order to have pizza, you actually have to come down. So that's that. For those of you who are in the back and are scared, you can come down, and then that will actually work. So we're going to bring a pizza. So that's like probably the thing.
Just ask a quick question.
Absolutely.
Discussion while you're going on pizza. One of the things that always bothered me about Bayesian analysis is it hits you with scientific numbers.
Right, yes.
When you're doing empirical science, numbers are error bars.
Right.
Very big error bars.
Yes.
It's important to realize that.
Yeah,
a better approach would be something that puts on realistic error bars and propagates the errors.
Right. And there are a number of ways that you can do it. I don't see that as an either or.
Yeah.
And so, but you're right. There is a tendency of trying to assign specific numbers. What I like to do is I like to see, try to compare it to other things. So, for example, the McGrews end up coming up with a 10 to the 44 kind of chance. 1 out of 1044 that didn't happen. And I'm like, okay, what would that mean? That would be like having a royal flush like 15 times in a row or something like that. I mean, it's that level.
Yeah.
And I'm like, there's no statement in science that is even remotely that well known. Right? You know, and so that's what we do. It goes from states where you can kind of show the number of sequence and any kind of sense. But you're right.
Kind of relevant question to this, but since you mentioned that the specialty is calculated in the Jewish Torah,
Okay.
so they always said that
Oh yeah. The numerology.
Yeah, sorry.
Yes, I have. And most of those, I mean, so there are special numbers
My bad, bro.
that come up a lot. 7, for instance, or 12, right? Come up a lot, right? You know, right? Because it's what the 12. The cycle, you have 12. The 12. Yeah, and also the 12. In Judah, the 12 districts, and then so there's like 12 kind of comes up all over the place, and because of 12 once in a year. So there are obviously like certain numbers that are important, right? But once you start doing that, and then you say, okay, are there any codes in this? That's where things are a problem, because you can easily, oh yeah, it does go. Or rather, it works, but you can do it with any text. You can basically go take Harry Potter off the shelf and count up letters and come up with some combination and some special combination. Right. Oh yes. No, that's a great question.
Thank you so much.
Oh, cat, no, right.
I think you should call it. This one is it says choose. Yes.
Oh yes. Okay. Yeah. How does it got? Yeah. It's a very optimistic outlook and very cheerful. It seems. Oh yeah.
Doing an alternative.
Okay.
Calculation. Mine was really pretty cheap.
Yeah. Oh yeah. Of course.
I came up with something like there's minus 17.
Yeah.
Right. I think Victor Sanger told me.
Oh, nice. Yes. Sure.
Either way.
Right. There are dangers, obviously, in trying to take something that's not quantitative and forcing it into kind of a quantitative platform. However, I do find that this mathematical structure of it allows me to structure how I think. Like it kind of says, it's not enough to know about how well your explanation fits the data, right? It's also like how well that explanation is before you saw the data, and then also the alternatives. Again, a lot of people don't really stress that enough, and you don't see that as much when you do models that are just like, positive God or not God, like kind of two bins, right? And really, both of those need to be broken out into other like separate models.
So the machine learning should have been pretty easy to prove that
Oh yeah. You can probably find it. It's kind of numerology codes, right? You can certainly, I think you can do just random. It's kind of like people would look for random correlations. There's a great website called Spurious Correlations that has like, the price of margarine correlated with like, depths in swimming pools or something like that, or like it's called Spurious Correlations, and there's some amusing ones. It's like the number of Nicolas Cage movies, and there's and like the number of strikes for steel workers or something. I mean, it's just completely unrelated. And all they did was just like they just ransacked a big database of just random data and just looked for trends that follow the same thing, and you can find it. So if you look for numerology codes in any book, you can do that, and that's kind of danger for any kind of numerology sorts of issues. So I find that like almost always the biggest problem that most of these approaches have is kind of lack of imagination in terms of the alternatives. And another one that comes a lot is the idea of simplicity. And these will often argue that God is simple, that is a simple explanation. And they're thinking that that simplicity has to do with kind of the number of properties or the number of components. And so in that case, something like the God explanation is simpler than say quantum field theory, right? Which has a lot, has a lot of components to it and so on. But that's not actually what the math says. So if you mathematically, probability theory says that simplicity has to do with the flexibility of models. So more flexible models are more complex. If you have more constrained models, then they are simpler. And in fact, you can get through what's called a marginalization process, where essentially if you have a model, say, that depends on a parameter, and you don't have any information about the parameter, you can integrate out that parameter, and that factors in the uncertainty in that parameter, and you can show that model will get a penalty due to its extra complexity. And because of that, you may prefer a simpler model. Now, it's possible that model fits so much better than the other one that it overcomes that penalty, so the complexity is justified. But after a while, the complexity might not be. And you can see this like in a regression case, where if you have some data, let's say you have 50 data points, and you fit to a line, you can fit to a quadratic or a cubic, and just keep going. If you fit to a polynomial that has 50 terms in it, you can get a curve that will go through every single data point and have a mean squared error of 0. Which, if you're trying to minimize it, that's the lowest you can get. But you've done it at the expense of having a more complex model. So if you did it kind of properly, integrating out your parameters, you find that the more complex models get penalized. So if you're taking something like the God hypothesis, God can pretty much do anything. So the God explanation pretty much has infinite flexibility, or such an outrageously large amount of flexibility that it is not a simple hypothesis. It's one that and it has essentially the same content as magic did. Magic is a single word, I can always say it, but it doesn't actually explain anything because it can't explain any outcome at all. And this is part of not being well defined, and it's part of just trying to having an explanation that is overly flexible. And this is something that I don't think is stressed enough. So whenever anyone says like, oh, the God hypothesis is simple, it's like, no, it's actually like super complex. It's just because it's flexible, not because it's So here's another favorite that others love to go against, and that is sometimes called Sagan's maxim. Tim McGrew actually talks about that in the video, calls it that. And he had extraordinary claims require extraordinary evidence. I first saw that probably in this Cosmos series, but he probably had it in a Demon Haunted World. It's a really great book where he talks about alien abduction. So he was introducing in terms of extraordinary claims like alien abductions and cross circles and things like that. But it's often applied to miracles. And then there are the biggest critique that often happens is it'll say, well, what does extraordinary mean? Right? If you don't say what extraordinary is, this doesn't really mean that much. But if we map the probability, we can actually understand exactly what it means. So imagine that we have an extraordinary claim that's probably has 0, and then all the mundane possible claims are going to lump into what I call N1. So if I want to say that the miracle is more likely than a mundane claim, that means that the posterior ratio should be less than 1 for that. This is like the odds form of that. The median of extraordinary for the extraordinary claim means that the prior is really, really low. That's all it means. So what does the extraordinary mean for the claim? It means the prior is super low. If we assume that the extraordinary claim itself fits the data basically perfectly, so you can have the resurrection hypothesis may explain, I say may, because it may not, but it may explain all the data, but you may have other cases. If you want to have the probability of your miracle larger than your mundane claims, mathematically you have to have the mundane claims explain the data so much worse than or basically comparably worse than the miracle itself. And so this is what it means to have extraordinary evidence is the fact that you need to rule out nearly every other mundane claim. Not just that it's unlikely, but you have to get to the point where it's really ruled out. So that's what. So Carl Sagan had this pithy quote, right? And you can probably critique the work on it, but it's just a pithy quote. What does it mean? Is that essentially claims with low priors need evidence enough to overcome the low prior. The methods of science pretty much address that. Right? The whole idea of designing experiments and so on is to rule out all the other possible alternatives. I remember I was really surprised when I was an early graduate student. I would go to these talks in the neuroscience department, and there'd be like an hour-long seminar, and the first 10 minutes was the explanation of, we measured this thing and we got the effect that we were expecting, and this is the conclusion that we got. And then the rest of the talk was, then we had to do this experiment to rule out this possible alternative, and then I had to do this experiment to rule out this possible alternative. And so the bulk of the talk was really about ruling out all of the alternatives so that we could be reasonably confident that the main conclusion was correct. And almost invariably, especially if it was early in a project, at the end, someone would raise their hand and say, did you think about this? Right? Some other explanation. And they were like, nope, I need to go back to the lab and rule that one out because it was a more mundane explanation than the one that they're saying, and then that became more likely. And this is a little of the process of science and how it works, and it fits within this kind of structure. And so I was just recently looking at, trying to do experiments that do this in kind of a major way. Trying to measure photon decays was one that came up, and I was just looking at the Wikipedia page about how the experiment is done. And so photon decay is one of the key predictions of some of the grand unified theories, but it's predicted to not happen in the standard model. So we actually have models that predict different things about it, but in either case, it's super rare. And so in order to actually measure it, they have to locate the lab like 1,000 meters underground. They have to keep recirculating the water. They have to filter for dissolved gases because you get alternatives. You have to remove radon because it's going to give you false signals. And so there's this whole laundry of things that they have to do in order to rule out all the alternatives. And this is just this is pretty much what happens in any experiment, whether it's big or small. This is the sort of thing that happens. We're essentially trying to write out as many explanations as you can, rule out as many of the alternatives as possible, so that the ones that derive are. So this brings us to testimony. The philosopher I think that apologists hate the most, it seems, is David Hume. In particular, he has this statement that says no testimony is sufficient to establish a miracle, unless it is of such a kind that its falsehood would be more miraculous than the fact that it tried to establish. So again, this is he wrote before Bayesian was around, and so his language ends up being a bit more flowery. But as you can, and there are various kind of critiques of this, but essentially it has the same mathematical structure. To kind of match it, it's essentially the same content as the extraordinary claims require extraordinary evidence. It's just that applied specifically to human testimony. And so when we see this sort of structure, it kind of falls naturally out of mathematics. It can actually make things clear. So where someone might criticize the way that someone might phrase it in English, it's a lot harder to criticize it when you can kind of show the structure mathematically. And that's the benefit of doing it. So I've seen this in a few places where it says, other than having a zero prior, if you have a small prior, there should be some amount of evidence that makes the particular explanation the most probable one, even if it comes in with a super low prior. There should be some amount of evidence that will bring you out of the low prior, right? And when it comes to kind of historical accounts, and they may talk about testimony. So someone would say, if you have enough independent accounts, then you can overcome any prior that you want to, right? So essentially, if you have something like this, this is structured like what the Magru's did, and you have a whole bunch of independent accounts, then if n is large enough, you can overcome any prior whatsoever. Okay? And I was thinking about this, and I like to and they say this is like a slam dunk against Hume, like boom, like you're saying, Hume says that, like, you know what, we're just not going to believe it has to, believe these claims because it's human testimony and it's unreliable, and so I can't, we can, and it's definitely more likely they're mistaken than a miracle. Like that's essentially Hume. And so the response is, wait, if we had like 100 of these things and they're independent, then we can overcome any prior we want to, right? That's the. So I started thinking about these things, and I like coming up with kind of toy problems, toy ways of doing it, kind of tease out some of one's intuitions. So what I decided to do is write a little mathematical model of this process of independence. And I was curious about like, one, how many independent attestations do you need to overcome a prior? That's one. And what if you're like not entirely certain they're independent? How does that factor into place? There's, you can say things are independent, but maybe they're not. Like even in the case of drawing cards, like most of the time the draws are going to be independent, and you kind of can see it. But you can easily have a magician. You could have deception. You could also like actually not shuffle it well, like a minute not shuffling well might do it, and so unintentional mistakes and that sort of thing. So I made a little model where I'm taking essentially the miracle probability as lowercase m, and just to kind of simplify the final equation. And so it's opposite is 1 minus m. And then I have some number of data points, and I'm going to assume for a second that they're independent, and that the ratio between them being true or not is 1,000. I took that number straight from the group. So I'm kind of reproducing that structure. And if I'm looking at and again, just kind of the likelihood ratios here, and that would be this term would be 1,000 to the end, and then this is my prior coming into play. So I can reproduce the McGrew's calculations fairly simply, but then so then I'm thinking, okay, that's the fully independent case. What happens if they're completely dependent? So I have n pieces of evidence, but they're all completely dependent on each other. That means I have one piece of evidence, right? Because knowing one, the next one doesn't tell me any information about the previous one. That's what it means to be dependent. And the third one doesn't tell me anything about the first two, and so on. And so essentially, I would get something like this, where that first term is never going to overcome the prior. So somewhere in between here, we may find ourselves in the question of where are we actually finding ourselves. So I add a parameter to say, like, okay, something beta is equal to 1, I'm going to be certain that they're independent. Beta is equal to 0, I'm certain that they are completely dependent. And anywhere in between, I'm somewhere in between dependence and independence. Okay? And so and then I can just look at the ratio of that given this kind of factor. And so if beta is 1, I reproduce essentially the McGrew's result. Beta is 0, they're completely dependent, that's probably unrealistic. But then I can, so I can do the McGrew's calculation. But then I can ask, how certain are we at, in terms of dependence? And this is a plot again. So this is essentially the log odds ratio. And depending on what your prior is, that would be some line that you need to cross on here. So like, so if the probability ends up crossing above like 10 or so, that's when the probability of the miracle then becomes more likely than the mundane. Notice, however, that if you are even the slightest bit unsure whether the sources are independent, you suddenly are way below your prior, and the miracle claim is not very well supported. So this is a case where you can say, in theory, if you had 50 independent sources, you could uncover the prior. But if you have any uncertainty that these are independent, then pretty much it ends up being unsupported. And you can see this in these kind of little toy mathematical problems that I do. So you can be supremely confident that all, say, 15, and we're doing this 15 sources are statistically independent, and you can be so confident at the 0.9995%, and still not be able to justify a miracle within the uncertainty. And so this is a kind of a layer of kind of abstraction that I don't think is often covered in these Whenever you're doing miracles, there's also for other issues like being not available and no proper time until that and so on. And I look into a lot of miracle claims and a lot of beautiful claims and a lot of various medical claims that we have. I did another toy model where I was thinking that if I have a whole bunch of claims and each time I investigate a claim, I find that the claim is false. So I was doing this as a series. So imagine that I have so this is actually like having a whole series of claims. This is very much like the Goose case, where I can recover a prior. But imagine that I have a claim, I investigate a claim, I find it's false. I investigate the next claim, it's also false. I investigate the next claim, it's also false. What am I going to think about the next one, right? And so because of this process of investigation, it can change the value of the probabilities that you're going to get given the next data point. And in fact, what you can have is so this gamma parameter kind of gives us how much of an effect that has. But you can essentially, like the high-low deck problem, where you can have the probability go up at first with new claims, and then eventually you're like, wait a minute here, like every single one of these is failing for various simple reasons, and so the probability will actually go down. And so it has this property that if you don't take into account these sorts of differences. Now I know the original time was 6 to 7. I think we took a break, whatever. How long do you want me to go? Because I want to make sure that I don't overstay, welcome and so on. But I know the time shifted a little bit, so I just wanted to confirm.
Do you think 10 is fine? A break was like 10. A break was like 10 minutes.
Yeah. So I think I have a whole bunch of different things that I can cover. So I want to make sure that we also have time for questions and things like that. So I want to make sure to do that. Yes, actually, I'm doing okay. Given this kind of investigation into testimony, so those two things. Here's a tweet from John Flashy, and he says, do you think testimony provides no evidence that a miracle is occurred? Or do you merely think that it provides insufficient evidence? Because then if it's the latter, would you agree that in principle, testimony could be of sufficient quantity and quality that is sufficient? Right? And I look at that, and I just think, whoever's writing that is doing a very naive kind of application of probability, where they're saying everything's independent, and one claim is the same as the next, and it just builds up and builds up and builds up until you can overcome any kind of prior for that. One thing that I haven't ever seen, and I've actually asked John actually for this, is just to estimate any of the changes in the probability given any of the claims. Like put any kind of numbers to it. All right, approximately how much more likely is it in these different cases? Because depending on if you look at for example the first blue curve that goes way up high, that essentially has a prior of 0.1 and has a reliability factor of 0.8. But the point here is though that you have to get somewhere around 10 different independent sources in order to raise the prior above, right? One should be able to make an estimate and say, how many actual pieces of evidence do I need to raise a particular prior up past the point where I can believe it? And do we actually have that? So if it ends up being 20, we definitely don't have that. I say, for instance, in the New Testament. If we're looking at claims in the New Testament, then we have a lot of dependencies that go along, and I don't think that they are often measured well. Okay. I looked into faith and trust. This is actually one of those ones where gets into pedantic territory. People use the word faith in multiple ways, and so I prefer often use belief without evidence, but most Christians don't do. There's also used as trust, and I would like to ask the question about is there any time you could actually swap the two words, faith and trust, in that and I have a post about mapping this onto decision theory, but I'm not going to go into that that detail. Let me just finish up actually with my conclusions, so that way I can take questions and kind of go through, because we're kind of coming back to the same sorts of messages. So the game I'm playing is essentially to try to map most problems of reasoning into probability problems. I think that probability kind of quantifies the structure of how we reason, and it also shows where like we might reason incorrectly. Anytime we have a cognitive bias, it violates one of the rules of probability. I think we can kind of highlight that. Hopefully it makes things less clear, sometimes it may not. But I want to stress that in any case that you're doing, making sure things are well defined, making sure that you have alternatives and that you take them seriously, because that has a much bigger effect than is often realized. And also the idea that you can have data that is super well explained on a certain model and introducing that data still drives that probability down because of the alternatives. And that I think is probably one of the more major lessons that we have here. You can get basically all of my writings and everything else at blais.github.io. You can follow me on Twitter and contact me there as well. But I'll stop there and take any questions or any other discussion. Thank you.
Yeah, so anybody wants to ask a question, just feel free to ask the question and project or come down here. Yeah, whatever. Everything's good, man. Okay. Yeah.
Have you ever been surprised? I guess in any of these cases when you're investigating these things?
Most of the time I'm surprised that the data is as bad as it is. So I'll hear things that are stated really confidently, and then when I look at the data, I'm like, really? This is what this is confident on? And so that has surprised me. I don't think I've ever seen a case where it surprised me in a way that would lean me toward any of these kind of theistic interpretations. Mostly, I find that there are things that are really ignored. Priors almost always ignored. Alternatives ignored a lot. And so I was trying to think if I think of something, but nothing there. I've been surprised by some results in probability where something doesn't go by my intuition. There are some that are notorious like that, like the Monty Hall problem is a classic example. The girl named Florida problem is another one that's even worse than that one. Really presses on your intuition. It's very tough. But even some of these toy problems that I like to play with, where I say, what would happen if we had a whole bunch of these independent things, but we were uncertain about it? How do we characterize that? And seeing the fact that the probability will go up and then down again, that kind of dynamic, you just rarely see that in any kind of covering of this topic. Yeah.
Your current religious beliefs based on statistical model.
I'm sorry, what was that?
Your current religious beliefs based on some sort of statistical model.
My current religious beliefs based on some statistical model. In a way, yes. In a way, no. I would say that most of people's reasoning, and including my own, is not done with math. But the idea of having kind of alternatives and things like that, and seeing which ones and testing them, I think that's kind of the basis for what I believe. For example, I was once I was having lunch with a student, and I looked up, and there was a clock on the wall, and it had the wrong time, and the second hand was being erratic, and I was like, yeah, that clock is definitely just completely broken. And the student looked at it and said, well, it's actually ticking out the right amount of time. It's just doing it erratically. So it would click forward and then wait 5 seconds, but then click 5 seconds and then wait 2 and then click 2. So it was just jumping, but jumping the right amount. And I looked at it and I was like, no, this is not that good. So then what did we do? We both pulled out our phones, both of us, mind you, and we both timed I put $1 down to I was like, that's something that makes it a little bit more interesting. Usually my bet is a nickel. That's my standard bet for something. But this one was $1, and I lost the $1 because it did turn out that the clock was ticking out the right amount of time. So I was wrong on that. But my belief in that was based on, so I had my initial observation, but my willingness to test it. To say what, I could be wrong, I could be right. How would we know? And how can we test it? And even on trivial things. And so I kind of go through life trying to do that. And when I see people trying to support a claim and they don't do that, that's when it raises red flags to me. So to me, I'm a scientist first, and the process of science is always about testing, whatever you think is true, and trying to find ways to show that you're wrong, and accepting it when you are showing you're wrong about these sorts of things. always being open to new evidence. I mean, someone wants to show me the new evidence for something, I'm certainly happy to look at it. So I investigated a ton of miracle claims, and they fall under pretty much only a few kind of bins. One where the data is literally just not available. People make a claim, but it's just a story, so there's no way you can investigate. See, there's plenty of things. Or the original claim was different than what it is now. So this happens a lot with UFO claims. So there's a famous case in UFO observation in Rendlesham Forest in England, and they saw a UFO and they chased it to the woods, and then there was they recovered a book from it. There were markings on trees and so on. And if you go back to the original report, all it was there was a light that they couldn't identify that they tried to chase through the woods, and that's it. That was the original report. That was all. And then all the other stuff kind of you see legendary development, right? And so that happens a lot. Or the timeline is just not well established. Like essentially, at some point they had this ailment, and sometime later they didn't have this ailment, and stuff happened in between. But like that stuff included prayer and going to the doctor and doing lots of other things. So you just literally cannot tell. You cannot establish that whatever what they did, what they're claiming that they prayed and then they got better, that you can't tie it to the thing. So the timeline is broken. So those are the things. Those are the things that I see, and not many exceptions beyond that. Yes.
You mentioned in the very first slide that you have strong opinions on pseudoscience. What do you mean by pseudoscience?
Okay, so pseudoscience is when someone makes a claim that they are not supporting properly, but they're often using the vocabulary of science to give them an air of authenticity. So if you say something like a lot of the sham medical treatments, like homeopathy, for example, is a good example of this. And they'll talk about scientific studies, and they'll talk about dosages and things like that, and they might have this kind of complex model about how when you reduce the amount of active ingredient, you increase the effect, and so on. They'll use fancy language and so on, but when you actually go and look at what they're doing, they're not actually following the rules of science. So that's what I consider science.
Second part of my question. What are your thoughts on previous scientific theories that were considered true that were later disproven with further evidence? So for example, like before we knew about oxygen, we had this theory of phlogiston,
yeah.
right?
Yeah.
And given the evidence at the time,
right.
It would have seemed to be the most
right. There was a time where it was perfectly reasonable to believe that the Earth was flat. There was a time where it was perfectly reasonable to believe that God created all life as maybe 6,000 years ago or 10,000 years ago or whatever, right? After Darwin, it will no longer be reasonable to have that, right? Because we've learned things. Like, yes, we can be wrong, right? Science is self-correcting. But there are some things that we're not going to be unwrong about. Like, there's some things that where, once we've learned it, there's not really kind of a way to kind of go back. There was a time when it was reasonable to think that the sun went around the Earth because everything that you could observe is entirely consistent with that observation, and anything else would actually be possibly more complicated, right? And so I don't see that as a conflict. People learn. That's the whole point of Bayesian is that you start off and you have probabilities and then you update it with evidence. Is that
right? But using your methodology for those theories, there are not many other alternative models. Hence, the probability of those theories being correct is fairly high, which is why people accept it.
Like what? Oh, because they didn't have many alternatives. Yeah, sometimes you don't have a lot. That's unfortunate but true. And then you can have things that you know really well, and you even know that they are wrong. So, for example, Newton's laws, right? When they were applied to orbital mechanics, and we have really, really confident that Newton's laws are correct. However, it was also known that Mercury had the precession of its orbit that was not explained by Newton's laws, but we didn't just ditch Newton's laws because we didn't have an alternative, right? Sometimes we know something's missing, but we don't have an alternative, and it's just like, okay, that motivates us to look for an alternative. I mean, I think that's good, but one should always be humble and know. I mean, for instance, currently, we know that Einstein's general theory of relativity is correct out to as far as we can possibly measure. We also know that quantum electrodynamics is also correct as far as we can measure, and we also know that they both cannot be correct because one is discrete, the other one is continuous. One is probabilistic, the other one is deterministic. We just know that they both cannot be correct. And so somewhere, and maybe we will never be able to get to that point, but probably at super high energies or some other division, we can start seeing that difference, and we'll try to do theories of that merge the two. But right now, yeah, we don't know, and we may not have a lot of alternatives. And so in certain domains, we can be really confident that these things work. In other domains, not so much. But I don't have a problem with that. I mean, there's always going to be stuff we don't know.
Thank you.
Okay. Oh wait.
I'll ask one more.
Sure.
Is there like any party or like is there scientific claims today that we generally believe as scientific that you've like run your analysis on and would say it's kind of invalid? Like, are there any parties claiming they're scientific?
So you're saying that do I disagree with anyone who makes
Or like,
are there any examples of claims that I think are wrong that are in the mainstream?
Yeah, is there like is there like some party that's consistently claiming and everyone believes them to be scientific, but like their methods are flawed, or there's some
yeah, I'm not sure. To come up with an example on the fly, I'm not sure if I can come up with one that's good for that. There are cases where sometimes people can either they can come off as more confident than they should be. Sometimes it's a miscommunication, and sometimes it's just that's the way it is. I'm thinking that in the early days of COVID, for example, there were a lot of claims made about its transmission, about the efficacy of masks, whether it could be transmitted on paper and other things, right? And there was a lot of guesswork involved, and at first, and then as we learn more, right, and we get ideally we get better, right? Science communication is very hard because I don't think the public understands the level of uncertainty that occurs, and they see scientists who talk about uncertainty as being waffling or as like, well, why should I believe this guy? Because they're saying that, well, maybe it could be this or maybe it could be that, right? They want to hear the person who says, it's definitely like this, right? And then if that turns out to be wrong, then they're like, or if we think like, it's most likely this because most diseases are like this. And then suddenly like you realize that, this disease is different in this way. And we're like, we have to shift, we have to change our beliefs, right? And in those cases, the public has, I think, a very hard time adjusting to that idea of like, people should be open to changing their beliefs based on new evidence, and that shouldn't be a bad thing. It should be considered I used to believe in this, and I got evidence, and now I believe in this, right? That should be good, that should be lauded, and a lot of times it's not. I'm not sure if I can think of good specific examples that address your point specifically, but if I do, I'll let you know.
Yeah.
Okay, cool. Yeah, thanks everybody for coming to our talk. Thank you, Professor. Yeah, feel free to grab some more pizza and hang out.
Yeah, I'll hang out here for a while longer. So
yeah, okay.